Good morning, everyone. Welcome to Guru Brahma classes for JE and NEET. We are in the chapter Ionic Equilibrium. In this session, we are going to learn about common ion effect, solubility, and solubility product of a sparingly soluble salt. Let's start the session. Here we are seeing a common ion effect. Common ion. You know what is meant by common, right? So common ion effect. Regarding definition, how is it defined? It is the phenomena means process in which the degree in dissociation of a weak electrolyte is decreased by the addition of strong electrolyte having ion in common to that of weak electrolyte. Right? An example is given: acetic acid dissociating into acetate ion and H+. Let us see in detail. Okay. Now, in this container, what do we have? Let us take what is present in this container. In this container, initially acetate ion, acetic acid is present. What is present? Acetic acid. So acetic acid CH3COOH. It dissociates into CH3COO minus and H plus. As it is weak electrolyte, we are writing both forward reaction and backward reaction. When it is weak electrolyte, there will be both forward and backward reaction. That means some molecules will be converted into ions, and ions again convert into undissociated molecules. Already we have discussed this concept that whenever an electrolyte is very weak, it will be reversible process, and at a certain time there will be equilibrium existing between dissociated ions and undissociated molecules. This already we have seen. What is this weak electrolyte? Acetic acid is a weak electrolyte. Already its degree of dissociation is less. Okay. Weak electrolyte. What is meant by weak electrolyte? Already we know that its whose alpha is less. What is alpha? Degree of dissociation. Its alpha is less. Whenever alpha is less, we say that it is weak electrolyte. Now, acetic acid is weak electrolyte. Into this container, which is where there is acetic acid, into this container, what I am adding? I am adding a strong electrolyte. What is added? Strong electrolyte is added. Let us add a CH3COONA. Right? Sodium acetate. What is this CH3COONA? Sodium acetate. I am adding CH3COONA. It is salt and it is strong. Salt and it is strong. What does that mean? Strong mean that it dissociates completely. Strong means that it dissociates completely. Now it dissociates completely into what? CH3COO minus, okay, plus Na plus. Why did we write in this color? Because to show that this acetate ion is common to that of ion which was produced by acetic acid, which is produced by acetic acid. See, acetic acid dissociate into what is this called as acetate ion. Here you are finding acetate ion. Here also acetate ion you see. Are you finding this? Now, when you have added a strong electrolyte into the container already having weak electrolyte, and the strong electrolyte dissociate to produce ion which is common to that of ion produced from weak electrolyte. So when you are adding the strong electrolyte, what is happening? Already acetic acid weak, it is weak electrolyte, its alpha is less. When you are adding sodium acetate, its degree of dissociation still decreases. Its degree of dissociation still decreases. That means its solubility decreases. Solubility decreases. So what you can write on adding, what you are adding? On adding CH3COO minus Na plus. What is this? Sodium acetate to the container containing acetic acid the alpha means what? Degree of dissociation of acetic acid decreases due to common ion. So what is the common ion here? Acetate ion is the common ion. Acetate ion is the common ion, right? Due to this common ion, what is happening? Degree of dissociation is decreasing. Due to decrease in the degree of dissociation, there is decrease in the solubility of acetic acid. So what you can write? Due to decrease in alpha, the solubility of acetic acid decreases. Solubility of acetic acid decreases. So what did you understand from here? We understood that there is weak electrolyte in a container. When you are adding salt, which is producing common ion on its dissociation, common ion means the common ion which is common to that of ion on dissociation of acetic acid. See, when acetic acid is dissociating, it is producing acetate ion. When sodium acetate is dissociating, it is also producing acetate ion. So these two acetate ion, both are acetate ions. Both are, we say that as they are same, we say common ions. They are called as what? Common ions. So due to release of this common ion, due to the presence of this common ion, the solubility of this weak electrolyte decreases. This is what common ion effect is. So the phenomena in which degree of dissociation of a weak electrolyte is decreased, whose solubility is decreased, whose alpha is decreased, acetic acid alpha is decreased. On addition of whom? On addition of sodium acetate. Why? Due to common ion. Understood? So this can also be explained. This is explained based on Lee-Chatwier's principle or the factors affecting the equilibrium position. Okay, so let us see. We know that in a container we have, what do we have? We have acetate ions CH3 COOH, on dissociation gives you CH3 COO minus plus H plus, right? It is a reversible reaction. After the reaction at a certain time, it attains equilibrium. Now it is in equilibrium. No doubt the destiny of a, or the destination of a reversible reaction is to attain equilibrium. Yes, it is in equilibrium. The rate of forward reaction is equal to rate of backward. Now, according to the factors affecting the equilibrium position, or based on the Le-Chatelier's principle, if you increase the concentration of the product, on increasing the concentration of the product, what happens? The net rate of backward reaction is favorable. Now, I can say based on Le-Chatelier's principle, on increasing the concentration of products, the net rate of backward reaction favors. That means what I can say, equilibrium shifts to left side, backward direction. Okay, this we know. If the reaction is moving in forward direction, we say that solubility of acetic acid is increased. If the reaction is moving in backward direction, we say that the solubility of acetic acid is decreased. Now, on adding acetate ion, the reaction is moving in backward direction. What does that mean? The solubility of acetic acid is decreased. Okay. Then what I can write? I can write that on adding sodium acetate, it dissociates into acetate ion and sodium ion. Okay, to whom you have added this? You have added the sodium acetate into the container. Already acetic acid is present. Already who is present? Acetic acid is present. Acetate ions, is that acetate ions from sodium acetate increases the concentration of acetate ions. That is product concentration. So, the net backward reaction occurs. That means solubility of acetic acid decreases. Alpha of acetic acid decreases. This is what the common ion effect is. So the net backward reaction occurs. This is all because of common ion. What is that common ion? Acetate ion. This is all because of what? Common ion, which is called as acetate ion. Understood? So this common ion effect can be explained by using the Le Chatelier's principle. Simple thing is that when you add salt to a weak electrolyte which contains common ion to that of ions produced from weak electrolyte, due to common ion effect, the backward reaction occurs so that degree of dissociation of weak electrolyte decreases, so that the solubility of weak electrolyte decreases. This is what the common ion effect is. What you need to remember? The weak electrolyte solubility decreases on adding salt to that weak electrolyte containing common ion. Simple thing. Okay, let's move. So here we are seeing what solubility. What is that solubility? What is meant by solubility? Let us see. The maximum number of grams of solute dissolved in 100 grams of the solvent at a particular temperature. The solubility depends upon the factor temperature. When the temperature changes, solubility changes. Right? Let us understand this. If you try to understand this, let us see. Here there is 100 grams of water, for example. What is present? 100 grams of water. Grams of water. So what will be it? It will be salt. Now I am adding salt, NaCl, for example. I am adding 1 spoon, 20 grams. Another spoon, 20 grams. So now when I add 1 spoon of NaCl, it is found that it has dissolved. Another 1 spoon dissolved. If you go on adding salt, will all the salt what you are adding, will it get dissolved in this 100 grams of water? No. For every particular amount of solvent, only particular amount of solute can be dissolved at a particular temperature. In this 100 grams of water, can you dissolve 1 kg of salt? Is it possible? No. So this 100 grams of water means here you will have water molecules, right? What are these? These are all water molecules. When you add NaCl, this NaCl moves into the intermolecular space. Na plus, Cl minus, Na plus, Cl minus. Where does this NaCl enter into? It enters into intermolecular spaces. And the intermolecular space in the water will be up to a certain quantity. It will not be infinite intermolecular space to dissolve infinite amount of salt. As there is less, or as there is a particular intermolecular space, only some particular amount of NaCl can be dissolved in this. For example, in 100 grams of water, something like 30 grams of NaCl can be maximum dissolved. If you add, for example, I am speaking, if I add some extra 5 grams, that means If I add 35 grams, 5 grams of that salt will not be dissolved, because the maximum amount of the salt that can be dissolved in 100 grams of water is only 30. Are you getting that? So now I am saying that, for example, if I say solubility of NaCl is equal to 30. What does that mean? Maximum of 30 grams NaCl can be dissolved in 100 grams of water, for example. That means 30 grams of NaCl is present in 100 grams of water, and that is called as a solubility of NaCl in water. Did you understand now? So, for every solvent, there will be a limit. Only that limit, up to that limit, it can dissolve the solute. Here the limit, example, 30 grams is the limit. That is, maximum of 30 grams of NaCl can be dissolved in 100 grams of water. More than that, it cannot dissolve. This is only example. Right? Did you understand? That is called as what? The solubility. Here solubility depends upon the following factors. One is nature of solute, nature of solvent, temperature, pressure. For example, let me dissolve salt in water. What is that? Water. See, water is polar solvent. Salt is ionic compound. Salt is ionic compound. We know that like dissolves like. Like dissolves. General statement, there are exceptions. We are speaking about general statements. Like dissolves like. What does that mean? Ionic compounds dissolves in polar solvent. Next, covalent compound dissolves in non-polar solvent. Now, when salt is dissolved in water, it dissolves. It dissolves. Now, let us take benzene. What is that? C6H6. What is this? Non-polar solvent. Non-polar solvent. Now, you are dissolving this salt, NaCl. Will it dissolve in this benzene? Is it possible? No. So, solubility depends upon the nature of solute. Here the solute is salt, so it is dissolving. Nature of solvent also. In a particular solvent, a particular type of solute dissolves. In a particular solvent, see, in benzene, now what did change? Solute remained same. Here is also, let us take NaCl. Solute is same, but solvent is changing. On changing solvent, is the solute dissolving? See, in water, salt dissolving. In benzene, is it dissolving? No, because we have changed the solvent. So solubility, here the solubility of NaCl is equal to 0. Solubility of NaCl in benzene is equal to 0. Whereas is it zero in water? No. So it is depending upon the nature of the solvent. For example, let us dissolve, if you try to dissolve covalent compound like iodine, when you dissolve iodine in water, is it dissolves? No, it does not dissolve. When you dissolve it in benzene or CCl4, it dissolves. Okay. So here solubility depends upon the nature of solute as well as nature of the solvent. Not only that, temperature also. When you increase the temperature, most of the substances, ionic solids, most, not all I can say, most of the ionic solids, solubility increases on increasing temperature. On increasing temperature, the intermolecular spaces will be increased due to more movement of the molecules. So more amount of the solute can be dissolved in the solvent. So temperature is affecting the solubility. So most of ionic substances, most ionic substances solubility increases on increasing water temperature. That means on decreasing temperature, automatically solubility decreases. Are you getting this? If you go on increasing temperature, the substance will be more dissolved. Right? Next, pressure. For gaseous solute. If you increase the pressure, see when you observe making of soda water, carbon dioxide is sent into water with high pressure. When you remove pressure over the water, you find dissolved carbon dioxide comes out in the form of bubbles. Not only that, let us open the soft drink bottle. When you open a soft drink bottle, you will find that some bubbles are coming out from the water or soft drink. What are those bubbles? Dissolved carbon dioxide gas. Why it is coming out? Because when you open the bottle, the pressure over that liquid decreases. When the pressure over the liquid decreases, automatically the dissolved carbon dioxide comes out in the form of bubbles. So that means on increasing pressure of gas over liquid, its solubility, that means solubility of gas increases because you are pressurizing it, and vice versa. Vice versa means when you decrease the pressure, then the solubility of gas over the liquid decreases. Understood? So this is about solubility. In this chapter, we are speaking about, in this particular topic, we are speaking about the solubility of ionic solids, and that too salts. Ionic solids are also called as what? Salts. Let us move to the next part. See, solubility of ionic solids in water varies with a great deal, changes. We are speaking about solubility of ionic solids in water, changes. Do all the ionic solids dissolve in water to the same extent? No. Some solids like, calcium chloride, CaCl2, are so soluble, that means highly soluble, that they are hygroscopic in nature. That means hygroscopic means they can absorb water vapor from atmosphere. Some ionic solids are highly soluble, like calcium chloride. Some solids like lithium fluoride have so little solubility, their solubility is very much less, that they are commonly termed as insoluble. Very much less soluble. Here solubility, see, the solubility of ionic solids depend on number of factors. Now only we have seen like nature of the solute, nature of the solvent, temperature. And not only that, important amongst which are lattice enthalpy of salt and solvation enthalpy of ions in the solution. Okay. So let us see that. Generally, ionic solids exist as crystals. They exist as crystals, crystalline form. Crystalline form means there will be proper arrangement of ions in the solid. In the solid, there will be proper arrangement of ions. Due to that proper arrangement of ions, they get a proper shape, so that we call them it as crystalline form. So ionic solids exist as crystals. Strong electrostatic force is present between oppositely charged ions. What is that term? Strong electrostatic force exists between ions in ionic solid. Okay. Now this ionic solid, for example, let us take NaCl or KCl, whatever it is, right? Here even CaCl2. When they are dissolved in water, so they exist in the form of a crystal. See, crystal. For example, let us take AB, solid AB, A plus B minus. Now what you are doing? You are dissolving it in water. So dissolving in water. For example, let us take water, because why we are taking water always? Because water is universal solvent. Now when you dissolve it in water, okay, these are very close. A plus and B minus are very close, because very strong electrostatic force is present between them. So they will be very close. When they are very close, when they are dissolved in water, water has dielectric constant 80. Water has dielectric constant is 80. Simply understanding what is dielectric constant means it decreases the force between the ions up to 80%. That means first step what happens is it will break into ions. AB solid is converted into A plus, and B minus. They are broken into ions. To break this into ions, some energy is absorbed, and that is called as lattice energy. We call it as lattice enthalpy also. What is called as a lattice enthalpy? Lattice enthalpy. Energy or change in the energy also we can take. Required to break 1 mole of crystal into ions. Why we are mentioning crystal here? Crystal means ionic solid. So enthalpy is always calculated for 1 mole. So to break 1 mole of ionic solid into its ions, how much energy is required is called as lattice enthalpy. Why energy is required? Because very strong force is present between the ions. To break that electrostatic force, energy is required. And that is what called as lattice energy. Lattice energy. So lattice energy is endothermic or exothermic? It is endothermic. It is endothermic because it is absorbed. What is that? It is endothermic. Energy is absorbed. Right? So after the formation of ions, what is formed? Now A plus is formed and B minus is formed. Now around A plus, what happens? This water surrounds. Water will surround. Water. A plus, no, oxygen comes near it. In the same way, oxygen comes near it. Oxygen comes near it. In this way, around this ion, water will be surrounding. This surrounding of water or water coming near to this ion is called as a solvation. When solvent comes near to a particular ion, and that is called as what? A solvation. Here as water is coming, when solvent comes, it is called as solvation. As water is coming, here we call it as a hydration. What do we call it as? Hydration. The same way here also, water comes near this ion. Not writing completely. Water in this way. Water surrounds this ion. Surrounding of water around a particular ion is called as water solvation. As water is surrounding, we call it as a hydration. If any other solvent surrounds, then that is called as solvation. In chemistry, we have studied that when two species come closer, energy is released. Here, what you find is when water is surrounding this ion, what happens is some energy is released. Energy released. What is that energy called as? Solvation energy. It is also called as hydration energy. Okay. So two processes are happening here. What is the two process? One is breaking of lattice. What is that? Breaking of a crystal or breaking of a ionic solid into ions and surrounding of solvent around these ions. During one process, energy is absorbed, and during another process, energy is released. Okay. Here, lattice energy is endothermic, whereas solvation energy, what is that? Solvation energy, which is also called as hydration energy, as water is surrounding this. Solvation energy is exothermic. So solvation energy is released energy. So solvation process is exothermic. Okay. Solvation, what we say, solvation process is exothermic. So when ionic solid dissolve in water, two processes are happening. In one process energy is absorbing, in another process energy is releasing. Okay, so these two process and these two energies majorly affect the solubility of ionic solid in a solvent. Which two process majorly affect the solubility of ionic solid in a solvent? One is lattice enthalpy, another is solvation enthalpy. Solvation enthalpy. Solvation enthalpy is also called as solvation energy. So in general rule, as a general rule, for salt to be able to dissolve in a particular solvent, its solvent energy, solvation energy must be greater than lattice enthalpy. In most of the solids, we find that if solvation enthalpy is greater than lattice enthalpy, ionic solid is soluble, more soluble. This is general rule. Exceptions will be there and all those, but in most of the ionic solids we find that if solvation energy or solvation enthalpy, that means hydration enthalpy, is greater than lattice enthalpy, ionic solid is more soluble. It is found to be soluble. Right? Let's move to the next one. So based on the solubility, already we have seen what is meant by solubility. Based on the solubilities, three types of salts we are finding. Category 1, soluble salt. But we say it is a soluble salt whose solubility is greater than 0.1 m. If its solubility is greater than 0.1 molar, so what is 0.1 molar? We can say that 0.1 molar solution, I can simply represent it as 0.1 mole solute is present in 1 liter of solution. Let us take a solution always 1 liter so that it will be easy to understand. 0.1 mole of solute is present in 1 liter of solution. Then we say that it is 0.1 molar. If the solubility is greater than 0.1 molar, then we say that it is soluble salt. If solubility is, what is that? Solubility of the ionic solid is less than, okay, greater than 0.01 m and less than 0.1 m, then it is called as a slightly soluble salt. We are classifying the salts based on the solubility. Based on their solubility. If the solubility is less than 0.1 molar and greater than 0.01 molar, then it is slightly soluble. Right? 0.01 molar means, what is that 0.01 molar? Here 0.01 mole solute is present in 1 liter of solution. Okay, then that is called a 0.01 molar. Already we have discussed what is meant by 0.1 molar. So such salts are called as what? Slightly soluble salts. And if solubility is, what you are finding here, solubility, if solubility is less than 0.01 m, those are called as sparingly soluble salt. So almost insoluble, but very small amount of the salt is soluble. A very small amount of the salt is soluble. That means its solubility is less than 0.01 m. Such salts are called as what? Sparingly soluble salts. And in this chapter, regarding solubility and solubility product, we are very much bothered about the sparingly soluble salts, the salt which is very much lesser soluble. So here whose solubility is greater than 0.1 are called as soluble salts. Example NaCl, KCl, BaCl2. And we are very much bothered about what are sparingly soluble salts. In this chapter we discuss about this. What are those? Whose solubility is less than whose solubility is less than 0.01. Is that 0.01, right? Like AgCl, AgI, BaSO4, PbSO4. What are all those? Silver chloride, silver iodide, barium sulfate, lead sulfate. All these are what are sparingly soluble salts. So let us take a saturated solution, and based on the amount of dissolved solute in solution, solutions are of three types. Dissolved solute in solution, solutions are of how many types? Three types. One is saturated solution, one is unsaturated solution, and another is a supersaturated solution. So simply understanding the saturated, unsaturated and supersaturated solution, let us understand. Already I mentioned that, for example, in 100 grams of water, 100 grams of water, solubility is 30. 30 means 30 grams of salt can be, NaCl can be dissolved in 100 grams of water. For example, let us take. So how much is present? 30 grams of NaCl is present. Exactly. Now, how much it can maximum dissolve? 30 grams. Yes, 30 grams is present. So it is called as saturated solution. So let us take another container. In this, how much water is present? 100 grams of water. Here only I dissolve 10 grams of NaCl. Now what is this solution? This solution contains solubility, salt less than its solubility. It contains solute less than its solubility. If a solution contains solute less than its solubility, then we call it as unsaturated solution. What is that? Unsaturated solution. Now let us take another container. Now here 100 grams of water, same 100 grams of water, but I dissolved how much? I dissolved some 32 grams of NaCl. Initially 30 grams dissolved, 2 grams did not dissolve. But when I heated it, 32 grams, extra 2 grams is also dissolved. So such solution is called as what? Supersaturated solution. Supersaturated solution. Did you understand? If the solution contains a solute equal to its solubility, then that is called as a saturated solution. If a solution contains solute less than its solubility, then that is called as unsaturated solution. If a solution contains solubility more than, if a solution contains solute more than its solubility, then that's called as what? A supersaturated solution. When can you prepare supersaturated solution? You can prepare by heating it. When you heat it, the molecules move randomly, the intermolecular space will be increased. So some more amount greater than its solubility can be dissolved, can be present in the solution. So that is the difference between saturated, supersaturated and unsaturated solution. Now in this we are very much concerned about what we are very much concerned about saturated solution. Saturated solution. So let us see that saturated solution. Let us consider a salt. Okay. What salt we are taking? Salt AB salt. Let us consider AB salt, for example. Okay. Like NaCl or AgCl. Let us take it as AgCl, for example. Now, I am dissolving this AgCl in this container. I am keeping this AgCl. How much AgCl I have kept here? I have kept some, okay, some 10 grams in water. What is all this? Solvent is water. Solvent is water. What is this? Solvent is water. So we know that AgCl, this AgCl is sparingly soluble. Sparingly soluble salt. Sparingly soluble. That means very less amount of this salt is dissolved. Soluble. Here, for example, among this something like, let me take 10 grams. Among these 10 grams, only 1 gram. What is this? Only this part. Only this part is soluble. Only this part is dissolved. So I am taking AgCl solid. Now among these 10 grams, how much is dissolved here? AgCl aqueous. 10 grams is dissolved. This dissolved 10 grams is in equilibrium with undissolved AgCl. Dissolved NaCl. And this AgCl is dissociating into Ag plus and Cl minus. Okay, Ag plus and Cl minus. This 10 grams is in equilibrium with its ions. With its ions. So in the solution, we are not bothered about the complete solid taken. We are not bothered about the complete solid taken. We are bothered about, or we are concerned with whom, how much it is dissolved. And that dissolved NaCl is in equilibrium with its ions. This part we are interested in the process concerned about this. Okay. How much is dissolved? All the solid is not dissolved. Only some of the solid is dissolved. This solid is dissolved into AgCl aqueous, and this is in equilibrium with Ag plus and Cl minus. We don't want the remaining 9 grams which is undissolved. We want the 1 gram which is dissolved. This dissolved AgCl, okay, is in equilibrium with Ag plus and Cl minus. Why? Because anyway it is sparingly soluble salt, very less soluble. So we find that there is an equilibrium existing between dissociated ions and undissociated. Undissociated. right? If I take here, if I consider here AgCl, AgCl, Ag plus and Cl minus, Ag plus Cl minus. Okay. You see, if 1 mole it is dissolved, how many moles of this is formed? Ag plus 1 mole and Cl minus is also 1 mole. 1 mole on dissolving AgCl. So this is this aqueous. Okay. This is also aqueous. This is also aqueous. 1 mole gives you 1 mole plus 1 mole. Right? If I give you this 1 mole per liter gives you 1 mole per liter and 1 mole per liter. Okay. If I consider S moles, what I am considering? S moles. Let me take it as S moles per liter was dissolved. Dissolved AgCl is how much? S mole per liter. Then how many moles of Ag plus will be formed? S mole per liter. And how many moles of Cl minus will be formed? S mole per liter, right? What is the solubility of AgCl? S mole per liter. If solubility is S mole per liter, how much Ag plus will be formed? What will be the concentration of Ag plus in the container? S mole per liter. And what will be the concentration of Cl minus in the container? S mole per liter. Because if it is 1 mole dissociated, 1 mole is formed. If it is S moles, then how many S and S moles are formed? Are you getting this? Let us move to the next part. This part is important, very much important. This part is very much important. You need to understand this part, right? You need to understand this part. Let us take Ag2CrO4, silver chromate. What I am taking, or otherwise in short form, let us take one more example. What I am taking, A2B sparingly salt. Now A2B is dissolved solid. Now this is dissociating into 2A plus B minus. Okay. Right. Then what you can write? If look here, 1 mole produces 2 moles and 1 mole. 1 mole per liter produces 2 moles per liter and 1 mole per liter. If I am taking S moles per liter, how much this will produce? 2 into S moles per liter and 1 into S moles per liter. Do you understand? Okay. That's the situation. Here, let us go with the next part. Coming to the next part, let us what is, now we are speaking about solubility product. What is that? Solubility product. It is the product of molar concentration of its ions in a saturated solution. In a saturated solution, there will be equilibrium existing between dissociated ions and undissociated molecule. There will be equilibrium existing between dissociated ions and undissociated molecule. This we know. In a saturated solution. So we can say that in a saturated solution, equilibrium exists between dissociated ions and okay, undissociated molecule. That is the reason why we have written this. Let us see this. For example, let us take here what he is asking, solubility products. AB salt. Let me take AB salt. Dissociates into A plus B minus, simple salt. Okay. So what is KSP? KSP is written as, saying that KSP is equal to the product of molar concentration of its ions. What are its ions? A plus ion and B minus ion. That means concentration of A plus into concentration of B minus. Simple thing. Okay. Let us go with another salt. A2B salt. 2 moles of A plus B moles of minus 2. See, how many you are finding? A2, 2A plus. Okay, now what will you write KSP for this? KSP is equal to A concentration of A power 2, because you are finding 2 here in the stoichiometric equation. 2 moles of A plus are there. So concentration of A plus power 2 you have to write. Are you finding? Then concentration of B minus 2. Okay. If I take some like AB3, then what will you write? KSP. KSP can be written as KSP is equal to, it dissociates into what? Dissociates into A plus 3 plus 3B minus. Okay. You know how charges are formed, crisscross method. Ionic solid, this is ionic solid, right? So KSP will be equal to concentration of what? Concentration of A plus 3, concentration of A plus 3 into concentration of B minus power 3, because in the balanced equation we have 3. Understood? If you go with A to B3, gives you 2A plus 3 plus, okay, 3B minus 2. What will you write KSP for this? KSP is written as A plus 3 power concentration power 2 and B minus 2 concentration power 3. Understood? So this is how we write KSP. In all these, what did we write? Product you have written. It is the product of molar concentration. Concentration expressed in moles per liter, molarity, of its ions. Whose ions? In a saturated solution. This is all for a saturated solution. Okay. And this KSP of salt changes with temperature. It varies with the temperature. For a general salt, it is given. Let us take a general salt. For a salt of AXBY gives you, see, how many X are here? How many A are here? X. X moles of A crisscrossing, you get plus Y plus Y moles of B minus X. Is it correct or not? This part you need to understand. When a salt with configuration AXBY is dissociating, it forms X moles of A plus Y plus Y moles of B minus X. See how this salt is formed. The salt is formed when A plus Y and B minus X are crisscrossed. In crisscross method, what do we do first? Let us remove the charges A, Y, B, X and bring the superscript as the subscript opposite crisscross. Then what do you get? AX, BY. You know this crisscross method? In that way, we have done it. Understood? Now, here 1 mole of this gives you X moles and Y moles. So, 1 molar gives you X molar and Y molar. If I take S moles per liter, then it gives you X into S moles per liter and Y into S moles per liter. Are you getting this? Can you understand this? One gives you, right? 1 gives you X, then S gives you how much? Crisscross S into X. Okay, this part also you need to understand, right? Now let us take, what is KSP? How do you write KSP? KSP of AX BY, this KSP is equal to concentration of A plus Y power X, because X moles no, and concentration of B minus X power Y. So now concentration of A plus Y you are finding it as X into S molar. So I can write X into S power X, and here it is capital M means what? Moles per liter. What is that? Moles per liter. Here YS, Y into S power Y. What is the concentration of A plus Y? We have found that the concentration of A plus Y is X into S moles per liter. Capital M means moles per liter. Here also capital M means what? Moles per liter. Understood? So if the solubility of the salt is S moles per liter, if the solubility of the salt is S moles per liter, then how many, what will be the concentration of A plus Y? It will be X into S molar. And what will be the concentration of B minus Y? It will be Y into S molar. So now KSP. So KSP is equal to X to the power of X into S to the power of X into Y to the power of Y into S to the power of Y. This you can understand, right? That is equal to X to the power of X into Y to the power of Y into S to the power of what? S, base is common. Then you can add the powers X, S plus Y. KSP is equal. So this is the formula to calculate what KSP. Then if I want solubility X plus Y is equal to KSP by X to the power of X into Y to the power of Y. Then I can write solubility S is equal to root KSP by X to the power of X into Y to the power of Y, which root? X plus Y root. Okay, so this is how we calculate. So you can find here solubility is equal to X to the X plus Y root KSP by X to the power of X, Y to the power of Y. So this is how. right? So let us move to the next part. Coming to the next part, let us see some salts. Some salts are given. AB type of salt. What is that AB type of salt? Let us take this AgCl. AgCl is also AB type of salt, right? So AgCl dissociates into Ag plus and Cl minus. If solubility of AgCl is S moles per liter, then it also forms S mole per liter, and it forms a S mole per liter. This mole per liter is written as capital M generally. How to write KSP? KSP is equal to Ag plus concentration into Cl minus concentration. Then that is equal to S into S. S into S. KSP is equal to S square. S is equal to root KSP. So for the salt of AB type salt, we have a solubility is equal to root KSP and KSP is equal to S square. Okay. Next, coming to second type of salt. What is that salt? AB2 type of salt. AB2 type of salt. Let us take one example. For AB2 type of salt, Ag2CrO4. Ag2, AB2 or A2B also you can take. Either of these will get saved. Ag2CrO4 dissociates to form 2Ag plus CrO4 minus 2. Okay. Now let us see S moles per liter on dissociating gives 2 S moles per liter and S moles per liter. Capital M means moles per liter. Here KSP for Ag2CrO4 will be equal to Ag plus concentration square into CrO4 minus 2 concentration. So Ag plus concentration you are finding it as 2S. So 2S square into S, that is equal to 4S square into S, that is equal to 4S cube. So KSP, what did we get? What did we get it as? 4S cube. Here you can find KSP is equal to 4S cube, and S will be equal to cube root of KSP by 4. Right? Let's move on next. For AB3 or A3B type of salt. Okay, so let us go with AB3 dissociate into A plus 3B, A plus 3 plus 3B minus. So what you can write? S mole per liter. Solubility of AB3 is S mole per liter. So how much A plus 3 we get? S mole per liter, and this will be 3S mole per liter. So then what is KSP? KSP will be written as concentration of A plus 3. What is that? Concentration of A plus 3 into concentration of B minus power 3, because we have 3 here. And this is equal to S into B minus 3 is 3S. So 3S whole cube. That is equal to S into 3 3 is 9, 9 3 is 27. 27 S cube. That is equal to 27 ES power 4. KSP is equal to. So KSP is equal to 27 S power 4. Okay. And what will be S? S will be equal to S to the power of 4 is equal to KSP by 27. And solubility. What is this S called as a solubility? So 4th root of KSP by 27. Understood? Okay. So let us see the next one. The next one is A3B2 type of salt. A3B2. So let us dissociate. A3B2 dissociates into 3A plus 2 plus, okay, what do you write? 2B minus 3. How many A are there? 3A. So we have written 3A. What will be the charge of A? Crisscross, you see, plus 2 and 2B minus 3. Okay. Let us see. If S moles per liter, if the solubility of A3B2 is S mole per liter, then what you get here? 3 into S mole per liter of A plus 2 is formed. 2 into S mole per liter of what is formed? B minus 3 is formed. Then what will you write KSP here? KSP is equal to concentration of A plus 2 power 3, because we have 3 here, and concentration of B minus 3 power 2, we have 2 here in the stoichiometric equation. So then KSP is equal to A plus 2 concentration is how much? 3S, and B minus 3 concentration is 2S. So what I can write here, 3S whole cube into 2S whole square. So 3 3 is 9, 9 3 is 27, 27 S cube into 4S square. KSP is equal to, then what do you get? 24, 27 into 4. 7 4 is 28, what do you get? 108 S power 5. So KSP, so here you can find KSP is equal to 108 S power 5. Then S will be equal to what? KSP by 108, okay, all power 1 by 5. Or that will be the answer, right? Okay. Next, let us go with the next part. So this is generally asked in the examination. Okay. So it is A3B4 type of salt, zirconium phosphate. What is this example? Zirconium phosphate. Zirconium phosphate. Okay. So Zr3 PO4 taken 4. Okay. Dissociation gives you 3 Zr plus 4 plus 4 PO4 minus 3. Right? So if the solubility of zirconium phosphate is S moles per liter, then the concentration of zirconium plus 4 found is 3S mole per liter, and the concentration of phosphate found is 4S mole per liter. Right? Then KSP, solubility product, can be written as zirconium concentration power 3, because we have 3 here, and phosphate concentration power 4, because in the stoichiometric equation we have 4. So that is equal to 3S whole power 3 and 4S whole power 4. What is this? KSP. That is equal to 27S cube into 4 4 16 16 4 64 64 4 4 4 16 256, right? So 256 S power 4. That is equal to, if you multiply this, what do you get? 6912 S power 7. KSP is equal to, then solubility will be equal to KSP by 6912 whole power 1 by 7. Understood? The relation between solubility and solubility product we are finding. So that is all with the session. Hope so you understood very well. I mentioned each and every symbol and a single point. You follow the classes so that you can understand it very well. Physical chemistry, mathematical, once again I am saying that mathematical operation is involved. So there will be several steps involved. There will be formulae involved. Application of formulae is involved, right? Follow carefully. Then you will be able to understand. Then you will be able to solve problems on physical chemistry. Thank you very much for watching.